For years, Microsoft has pursued a radically different vision for quantum computing. Instead of simply trying to build larger and larger quantum processors, researchers have been investigating whether quantum information could be stored in a special physical state that is naturally more resistant to disturbances. At the center of that strategy is the Majorana-zero mode. Quantum computers operate according to rules that are very different from ordinary computers. A conventional computer stores information using bits that take the value of either 0 or 1. Quantum computers use qubits, which can occupy combinations of quantum states and become entangled with one another. That flexibility could eventually make quantum machines extremely useful for certain difficult problems involving chemistry, materials, optimization, and other specialized calculations. But there is a major obstacle. Qubits are fragile. Heat, electromagnetic interference, microscopic imperfections, and interactions with the surrounding environment can disturb quantum information. This process, known as decoherence, is one of the biggest challenges in building a practical quantum computer. Most approaches try to overcome the problem through quantum error correction. Microsoft has pursued another possibility: topological quantum computing. The basic idea is fascinating. Rather than storing quantum information in a way that is highly sensitive to local disturbances, researchers hope to encode information into a more protected structure. This is where Majorana physics enters the story. Majorana-zero modes are predicted quasi-particle excitations that can emerge in certain engineered quantum materials. They are not simply ordinary particles floating around in space. Instead, they are collective quantum states that can arise under carefully controlled conditions. Scientists have explored structures involving semiconductor nanowires combined with superconducting materials. Under the right conditions, theoretical models predict that special zero-energy states could appear near the ends of these structures. If researchers could reliably create and manipulate such states, they might eventually become the foundation of topological qubits. The attraction is obvious. A qubit with greater intrinsic protection could potentially reduce the enormous amount of error correction overhead required by other quantum architectures. But there is a catch. Seeing a signal that resembles a Majorana-zero mode does not automatically prove that one has been created. Other physical effects can generate similar experimental signatures. Disorder inside the material, imperfections in the device, or ordinary electronic states can sometimes imitate the behavior researchers are looking for. That made experimental verification one of the most difficult parts of Microsoft's strategy. The scientific community became especially interested after researchers reported measurements that appeared consistent with Majorana-related physics. However, the results were heavily scrutinized. Eventually, serious concerns emerged regarding the analysis behind one influential result, and the associated paper was retracted. That was a major setback. But it is important to understand what a retraction does, and does not, mean. It did not prove that Majorana-zero modes are impossible. It did not demonstrate that topological quantum computing cannot work. Instead, it meant that the specific evidence presented in that research could not support the original conclusions strongly enough. For a field as challenging as quantum physics, that distinction is crucial. A promising signal must survive repeated testing. Independent experiments need to reproduce the result. Alternative explanations must be eliminated. And eventually, researchers must demonstrate that the quantum states can actually be controlled and used for computation. Microsoft continued working toward that goal. The company invested in materials research, device fabrication, measurement techniques, and the broader architecture required for topological quantum computing. The ambition remained enormous. The ultimate goal was not merely to detect an unusual quantum state. It was to turn that state into a reliable computational building block. And that is where Microsoft's next major step would become important. In 2025, the company announced Majorana-1, a quantum processor designed around its topological approach. The announcement generated enormous interest. But Majorana-1 should not be confused with a fully fault-tolerant quantum computer capable of replacing today's machines. The real scientific challenge remains much larger. Can these quantum states be demonstrated convincingly? Can they be controlled? Can they be connected together? And most importantly, can they eventually perform useful calculations while preserving quantum information? Those questions define the next chapter of Microsoft's quantum experiment. And the answer could determine whether one of the most ambitious ideas in quantum computing becomes a technological breakthrough, or remains an intriguing scientific pursuit. The announcement of Majorana-1 did not suddenly solve quantum computing. Instead, it represented another step in Microsoft's long attempt to build a fundamentally different type of quantum processor. The central idea remains the same: create quantum states that could provide greater protection against errors at the hardware level. If that works, the consequences could be enormous. Today's quantum processors can demonstrate impressive experiments, but scaling them into powerful, reliable machines is extraordinarily difficult. Adding more qubits is not enough. A useful quantum computer needs qubits that can maintain their information, interact accurately, and be measured without introducing unacceptable errors. This is why the phrase fault-tolerant quantum computing matters so much. A fault-tolerant system would use carefully designed methods to continue operating even when individual components experience errors. Topological quantum computing proposes that some of this protection could come from the physical structure of the quantum states themselves. That is the promise behind Majorana-based approaches. But promise is not the same thing as proof. The history of this research demonstrates why scientists remain cautious. A measurement can look exactly like the signal researchers expect and still have another explanation. That is why demonstrating Majorana zero modes requires much more than a single unusual electrical measurement. Researchers need multiple independent tests. They need to examine the behavior of the system under different conditions. They need to eliminate conventional explanations. And ultimately, they need to show that the resulting states possess the properties required to encode and manipulate quantum information. Only then does the technology move from an interesting physics experiment toward a practical computing architecture. If successful, the potential applications of large fault-tolerant quantum computers could be significant. Quantum processors may eventually help researchers model complicated molecules, investigate new materials, improve certain optimization problems, and explore chemical systems that are extremely difficult to simulate using classical computers. There is also a cybersecurity dimension. A sufficiently powerful fault-tolerant quantum computer could threaten some widely used public key cryptographic methods. That does not mean today's quantum computers can suddenly break the encryption protecting the Internet. They cannot. The concern is about future machines powerful enough to run algorithms capable of attacking certain mathematical systems. That is one reason governments, researchers, and technology companies are already preparing for post-quantum cryptography. But there is another misconception worth clearing up. Quantum computers are not simply faster versions of classical computers. They will not automatically outperform ordinary computers at every task. Their advantage comes from using quantum mechanics to solve particular classes of problems in ways that can offer major improvements under the right circumstances. So the quantum race is not simply about who can advertise the largest number of qubits. The real challenge is building useful, reliable, controllable, scalable qubits. That is precisely why Microsoft's strategy is so ambitious. If topological qubits can genuinely provide strong protection against certain errors, they could potentially reduce some of the enormous engineering burden associated with quantum error correction. But if the underlying physics proves too difficult to control, the advantage could disappear. This is why the earlier experimental controversy remains important. Science advances through skepticism. A remarkable claim must survive attempts to disprove it. Independent researchers must be able to reproduce important results. And theoretical predictions must eventually match experimental reality. Majorana 1 therefore represents an important research milestone, but it should not be described as the final arrival of practical fault-tolerant quantum computing. There is still a long road ahead. Microsoft has a bold hypothesis. Other companies and research groups are pursuing very different quantum architectures. It is still impossible to know which approach will ultimately dominate. Perhaps topological qubits will prove to be the breakthrough researchers have been waiting for. Perhaps another architecture will reach practical scale first. Or perhaps the final quantum computer will combine ideas from several competing approaches. For now, the most interesting part of Microsoft's story is not whether the company has already solved quantum computing. It hasn't. The fascinating question is whether Majorana physics can survive the enormous burden of experimental verification and eventually become a practical technology. If it does, the consequences could extend far beyond one company. It could change how we approach chemistry, materials science, medicine, optimization, and cybersecurity. But before any of that happens, the physics must come first. The signals must be real. The quantum states must be controllable. The results must be reproducible. And the machine must ultimately demonstrate something far more important than a dramatic announcement: reliable computation.